Okay, so okay, so we have, let's see, is this recording or not? Is it recording? Is it not recording? It's not quite clear. Recording, I guess. Stopping the sound. So today we're practically going to finish everything related with interference and diffraction of light, of sound, not light, yes. And this material is going to be useful also in the second semester where, when we're going to talk about interference and diffraction of light, of electromagnetic waves. So the concepts are not very complicated, and you're going to understand them just by looking at some pictures. So maybe let's start with some simple diagrams representing the interference phenomena of sound waves, like right here in this diagram. What's happening? So in order to have interference, you need at least two sources of waves, in this case, sound waves. And those two sources of sound waves have to either emit the same frequency and be in sync, in phase, coherent, the other word saying the same thing, or they just have to be a single frequency, a single wavelength is the simplest illustration. And this is what you have on this diagram. So you have two sources, and you have the two sources are emitting a single frequency, a single wavelength, and the same wavelength for the two sources. Now, in points like point C, the two waves arrive at maximum, minimum, maximum, minimum. So at point C, you have constructive interference. The condition for constructive interference is that the path difference between the two paths of the sound waves is equal to integer number of sound waves. I'm going to write it in a minute to report. Alternatively, at points like point D, the dark blue source comes at a maximum, while the lighter blue source emits a sound wave that arrives there at a minimum. So the maximum and the minimum cancel each other completely or partially, and the result is that observer located at point D is either not going to hear the sound at all, or the sound is going to be with very reduced volume, reduced intensity. The condition for constructive interference is that here is the first source, the second source, maybe the point of interest here. So if this first path is L1, the second path is L2, the path difference delta L defined as the difference between L2 and L1 may be taken in absolute value in order to ensure that it is a positive number. When delta L is integer number of wavelengths, and could be 0, 1, 2, and so on, you have constructive interference at that particular point. If the point satisfies the condition that the path difference delta L is semi-integer number of wavelengths, you have destructive interference. And we said that noise canceling headphones exactly use this destructive interference phenomenon in order to reduce or completely cancel the noise. Any remarks about interference?
Is there a difference between like harmonics and constructive interference?
So we're going to talk about standing waves, first harmonic, second harmonic, and so on in a minute. Well, the standing wave phenomenon that we're going to talk about is an example of interference, and it is, well, is it constructive or destructive? In some places it is destructive, in some places it is constructive, and it creates a nice stable pattern that we're going to talk about when the time comes. Okay, other remarks? I want to show another nice representation of Doppler effect. The Doppler effect that we talked about in chapter 16. Look at the following diagram, maybe right here. You have a single source of sound at rest, and you see the sound waves, the crests of the sound waves are represented with the blue circles. And of course, those blue circles are expanding with the speed of sound. And of course, new blue circles are constantly generated. Now, look what happens if the source is in motion. If the source is in motion and the observer is located here, he's going to detect, he's going to hear a shorter wavelength, higher frequency, increased pitch. If he's located here so that the source is moving away from him, he's going to detect a longer wavelength, lower frequency, lower pitch. Typical example of Doppler effect. Now, look what happens if the source of sound is moving fast. Here it is. You see that if the source of sound is moving with the speed of sound, the high pressure crests are on top of each other right here. And if he exceeds the speed of sound, look what happens in that case. This high pressure crests are on top of each other. This means that you have very high volume at that position. But of course, this high volume crests don't stay here. They move with the speed of sound. And if you're observer somewhere here, you're going to hear the sonic boom. This high pressure region that is formed by multiple high pressure crests on top of each other, you're going to detect, you're going to hear it as a sound, as a sonic boom. A shock wave that we call sonic boom. Okay. Any issues, comments, remarks about this? So let me prepare the next slide for what I wanted to talk about. Maybe this. Oops. Well, we talked about interference. Today, we started talking about diffraction. Let me see, where is this? Okay, this picture is what I'm going to need. So look, we talked about you have interference, but a closely related topic is the topic of diffraction. And last time we talked about a diffraction from a rectangular opening. So you have a rectangular opening with width capital D and sound waves, or any other waves for that matter, coming horizontally here. And diffraction is a phenomenon in which this linear propagation of waves is distorted by the presence of an opening or obstacle, in this case, opening. So what happens here is that the sound waves, after they go through the opening, they change the direction of their propagation. They start, some of the sound wave intensity is deflected to the sides. And as a result, the sound waves propagate not only in horizontal direction, but they also change their direction of propagation, at least partially. And as a result, the sound intensity is going to be distributed in relatively wider region right here. So you have, again, highest intensity at the center of the opening, but the intensity is going to drop slowly, and it is going to reach zero intensity at points like this. After that, you are going to discover that you have a secondary maximum, which usually is much smaller than the primary maximum. But for all practical purposes, you can assume that almost all of the energy of the wave, almost all of the intensity of the wave is going to be located between the two silent spots, between the two silent zero volume points. And last time we said that the angle at which this zero volume spot appears, that angle is given with sine of the angle is equal to lambda divided by d. Lambda is the single wavelength of the incoming sound wave, and d is the width of the rectangular opening. In a similar manner, if the shape of the opening is circular, you can demonstrate that the angle at which the silent point appears is given with a similar expression. Sine of that angle is 1.22 times lambda divided by d. Very similar. D now is the diameter of the circular opening. So this diffraction phenomenon is used in acoustics, in loudspeakers, and it is, of course, something that is very useful when you analyze, for example, resolving power of a telescope or a microscope or some other optical instrument. So knowing this, let's do some examples from the homework assignment on chapter 17. Let's start with homework problem problem number 8. So this is problem number 8 from chapter 17. It's a problem that is asking about interference, destructive interference of sound waves. And in this problem, they give the geometry of the setup in a way to help you solve the problem without using the law of cosines, for example. So here is the problem. You have two sources of sound, loudspeakers, separated by a distance, call that distance L, equal to, well, not L, L is reserved for other purposes. Make this distance D. The distance D between the two speakers, for my version, it is 5 meters distance between the two, 5 meters distance between the two sources of sound. And the observer, they say, is located at 90 degrees. So this angle is 90 degrees. And the observer is located somewhere here. Well, instead of, notice that the condition for destructive interference is written in terms of wavelengths. They don't give the wavelength of the sound, they give the frequency. But you can immediately say that the wavelength is equal to the speed of sound divided by the frequency. So they give you the wavelength indirectly. They give the speed of sound also. And they're asking for the largest possible distance between the speaker B and the observer, so that the observer to be in a point with destructive interference. So say that the distance between source B and the observer, call that distance L1, call the distance between the other source A and the observer, call that distance L2. You see that a right triangle is formed, and you can say that the distance L2 is equal to square root of d squared plus L1 squared. So the problem is asking us to find the distance L1, and they want we to find the maximum distance. So we have to set up the equation and look for a solution of that equation that has maximum value. And well, how to do it? The path difference between L1 and L2, so that path difference without absolute value, if you write it like this, L2 minus L1, L2 minus L1, you want that path difference to be integer number of wavelengths, a semi-integer number, right, for destructive interference. N plus 1/2 times the wavelength. The wavelength is known. You are looking for the distance L1. This is your unknown. Now, you can substitute L2 with its equal, and the equation now is going to look like this. Square root of d squared plus L1 squared. Now this L1 I can put on the other side of the equation, positive algebraic sign. Now square both sides of this equation. Remember, the unknown here is L1. This is what we want to determine. So square both sides, you get d squared plus L1 squared is equal to, so when this side is squared, you're going to get the following terms: n plus 1/2 squared lambda squared plus 2 times L1 times n plus 1/2 times lambda plus L1 squared. Now, the unknown L1 squared cancels, and you have the unknown only here in this term. And therefore, it is a linear equation, and you can immediately write its solution. So you're going to get that, let's say, move everything to one side of the equation, everything that doesn't contain the unknown on one side, everything that does contain the unknown on the other side of the equation, and you're going to have 2 times L1 n plus 1/2 times lambda is equal to n plus 1/2 squared lambda squared minus d squared. And now solving this equation for L1, you find that the distance L1 that they ask us to find is given with L1 is equal to n plus 1/2 squared lambda squared minus d squared divided by 2 times n plus 1/2 times lambda. And this is the answer. Now, this answer is not unique. Any integer number n is going to give you a valid distance L1 where you have destructive interference. So there is no general system of solving equations of this type, equations that are telling you to find only integer values of some number. So those type of equations usually are solved by trying different options. So once you have this expression, you have to set n equal to 0 first and find the corresponding L. After that, n equal to 1, find the corresponding L1. N equal to 2, find the corresponding L2, and so on. And you're going to see that L1 is initially going to be rising, and after that, it is going to start dropping. And you have to select the value of n that gives you the largest possible distance L1. So usually, so I can probably make some educated guess where that value is going to be. It is probably going to be either n equal to 2 or n equal to 3. But again, the best way to find that value is by trying different options. Okay, let's see questions and remarks. Yes.
So you mostly just do a guess and check sort of thing at the end?
Yes, there is no other way. Again, there is no universal method of solving so-called equations of Diophant, some Greek philosopher that was going with, I don't know, flashlight or something. But again, when I look at the equation, I probably can make a guess. For you, the easiest way is just to try different options. Yes.
So can you explain again how we know when we found the right answer?
So so n here is integer number, positive integer number or 0. So start with n equal to 0. You're going to, when you substitute n equal to 0 here, you're going to get one value of L1. After that, do the same thing, but with n equal to 1. You're going to get a different value of L1. After that, with n equal to 2, n equal to 3, you're going to see that L initially is going to start increasing as you try different numbers, and after that, it is going to start decreasing. You take the highest value. Once you see that L1 is decreasing, this means that you have already passed the maximum value.
Okay.
Yeah.
So I know this class isn't calculus based, but could you use calculus to find the answer without having to guess?
Yes, you can, but calculus is going to give you some rational number or even irrational, some real number for n. And this is why there is no universal way of solving equations of Diophant. Yeah.
For n equals 2, we're still solving for L1, right?
Yes, always solving for L1. L1. Oh, I misspoke here. Every time L1. Right? Every time. This is what is the unknown. So usually n equal to 2 or n equal to 3 gives you the highest L1. But again, you have to try with the calculator. Different people have different values of the distance d and of the wavelength, so you're going to have different answers. Yes.
Can you remind me what and the definition of the n is, or what n
N
represents?
is non-negative integer number. N is either 0 or 1 or 2, and it is just integer number. N is the integer number that makes sure that the path difference delta L is equal to integer number of wavelengths for constructive interference and semi-integer number of wavelengths for destructive interference. Other remarks and questions? If not, let's do problem number 10 is a problem about diffraction from an opening. So let's solve this problem number 10. So in problem number 10, you have a loudspeaker, so-called diffraction speaker, with rectangular opening. And let's see what they're saying. They give the size of the rectangular opening of the loudspeaker. Remember, the formula is that the diffraction minimum appears at an angle theta given by sine theta is lambda divided by d, where d is the width of the rectangular opening. So in the problem, you have the following situation. Here is the opening of the diffraction speaker. So the sound waves are coming here. The width of this opening is capital D. And the front row where the observers are is located right there. And they give the size of the rectangular opening. For me, that size is 0.076 meters. So for my version of the problem, G is 0.076 meters. And they give the distance between the speaker and the observers, the first row. And for me, that distance is 8.5 meters. So this distance is called that distance, maybe call it, select any letter, A, distance A equal to 8.5 meters for my version. So here is the center of the rectangular opening and the projection of that center on the first row. And you know that the sound intensity is going to be distributed along bell-shaped curve. And they're asking about the distance between this silent point and this silent point, that distance. Well, here is the angle at which the silent spot appears. The angle theta is right here. And you formed a right triangle. One side of the right triangle is the side A equal to 8.5 meters. And if you call the other side of the right triangle X, this right triangle now is completely determined because you know the angle and you know one side, right? You know that the angle has a sine equal to lambda divided by d. And therefore, you can determine this angle. The angle is equal to inverse sine of lambda divided by d. So now, a right triangle with one side given and one angle given, you can say that tangent of that angle is equal to the unknown distance x divided by the adjacent side a. In other words, the distance x is going to be equal to a multiplied by tangent of the angle theta. And web assign wants you to double that distance, and you have 2 times x is 2 times a tangent of the angle theta. This should be the answer for the problem. So keep in mind that this diffraction phenomenon occurs with any type of wave. And it also occurs not only through obstacles, not only through openings, but through obstacles. So instead of opening, if you had a rectangular obstacle, you would observe the same type of diffraction pattern. And it is a very useful device to analyze optical devices. Let's see questions and remarks about diffraction, interference, or anything else. Yeah.
With that formula, so we know A, the distance of the seats from the loudspeaker.
Yeah.
So other than that, though, we don't know X, right? X is what we're trying to figure out.
Yes. So yes.
Okay, and then how do we get to our, or how do we find our angle again?
Here is the angle. The angle is arc sine of the wavelength divided by d, and the wavelength is the speed of sound divided by the frequency that they give you. For me, the frequency is 30,000 hertz. Well, that's no, this is not a normal frequency, right? Well, this is ultrasound, but this is the 30,000 hertz, 32 hertz. This is a weird number for a sound that people can hear, but maybe this diffraction loudspeaker was designed to play music to your dog, for example, or your cat. So, okay. Other remarks and questions?
I don't remember which question it is, but there's one about if there's 2 openings. I think it's maybe like 7 or something like that.
This one?
It's like if there's two doorways that are open. And I was able to figure it out, but I kind of like to go over it again.
Didn't we
Yeah, I
solve
think
it?
it's 12. I think it's 12. Or wait, no. Yeah, I'll see if I
It's 9.
It was 9? Okay.
Didn't we solve it last time? No? Okay, problem number 9. Problem number 9. So it is a similar diffraction type of problem. So problem number 9. So you have a door with given width. Frequency of the sound is given. The speed of the sound is given. The diffraction angle. If you have one door open. Well, so again, here is the diagram, and let's say capital B is the original single door width of the opening. The sound waves come here. And on the other side, they form a diffraction pattern. The minimum of the sound is at angle theta right here. And this angle theta satisfies the condition. Sine of that angle is wavelength divided by this single opening width. Here again, the wavelength is the speed of sound divided by the frequency. They give the frequency again, but this time it is a sound that you can hear. So they're asking for the value of the angle theta in degree. So make sure that your calculator is in degree and say the angle theta is the inverse sine of lambda divided by d. So this is part A of the problem. Now part B, you double the size of the rectangular opening. And in part B, the angle theta prime, let's say, is going to be arc sine of lambda divided by 2 times d. So 2 times d under the inverse sine. And this should give the answer.
So you just act as if it's a bigger opening.
So if the opening is bigger, sine of the angle drops, and you're since the sine function is increasing in this part of the range, you're going to have decrease of the angle. Therefore, you increase the opening size, but the range where you can hear the sound drops.
What if you had one rectangular opening and one circular opening, just hypothetically, what would you do?
You cannot do it simultaneously, right? You either go through one opening, one shape, or another. Now, if you have opening with some irregular shape, part of a rectangle, and next to it, part of a circle, you cannot even, you don't have a formula that works for those cases. You have to become a physics major in order to solve the equation. Numerically, usually, you cannot solve it. So this is a good opportunity to become a physics major if you want to know what's going to happen with some irregular shape opening. Okay, so in the remaining 10 minutes, let's talk about the last topic from chapter 17 is standing waves. And we're going to start with standing waves in a string with 2 fixed ends. Here, 2 fixed ends. And in order to understand how standing waves are formed, look what happens if I create a disturbance at one end, let's say, with my hands, just moving my hands up and down very fast. I'm going to create a wave that is moving to my right. Once that oscillation, once that wave reaches the fixed end, it is going to get reflected and start coming back. But if I continue creating new waves, I'm going to have constantly waves that are going this way because I'm creating them, and waves that are reflected. The 2 waves are going to travel in opposite direction, but they're going to travel in the same space, in the same string. Therefore, I'm going to have conditions for interference of the wave that I generate and the wave that is reflected from the ends. If the wave I'm generating is with the right frequency, the interference is going to create a stable pattern in the string. And the first stable pattern that you're going to observe, that you can observe actually, is going to look like this. So the first stable pattern, the first harmonic, so-called, is going to be a pattern in the string that looks like this. In other words, if I select the right frequency of the wave that I'm generating, I'm going to have the first standing wave pattern is going to be a string that oscillates like this. So that you see that this is kind of a sine type of function. You can double it, and you can see that the wavelength is going to be equal to 2 times the length of the string L. In other words, the wavelength of the first standing wave, the first harmonic, so-called the fundamental, is equal to 2 times the length of the string. So after that, if I happen to choose a frequency that is twice larger, so I do this twice faster, you're going to see another stable pattern formed from the wave that I'm creating and the wave that is reflected. And that stable pattern is going to look like this. In other words, the string is going to oscillate with relatively high amplitude in those points, and it is not going to oscillate in the middle at all, and in the 2 fixed ends, of course. So, by the way, the places where you have maximum amplitude of oscillation, here in the middle or here at those 2 points, those places are called antinodes. And the places that you have no oscillation, here, 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 and those places are called nodes. Since we're talking about a string with 2 fixed ends, at the 2 fixed ends, you always are going to have nodes. And the first harmonic is going to have only those 2 nodes and 1 antinode in the middle. The second harmonic is going to have 3 nodes and 2 antinodes. You see that the wavelength of the second harmonic is exactly equal to the length of the string. Similarly, if I increase even further the frequency of generating the wave, I can observe a third stable pattern, third harmonic, that satisfies the condition. The third harmonic is going to satisfy the condition. It is going to be, what is it? The wavelength is going to be 2 times L divided by 3. Right. And so on. Yeah. The nth standing frequency that you can observe in a string with 2 fixed ends is going to have wavelength equal to 2L divided by n. So traditionally, this formula for standing waves in a string is written not in terms of wavelengths, but in terms of frequency. And since frequency is equal to the speed of propagation of the wave divided by the wavelength, you say that the nth standing wave frequency, the nth harmonic, is equal to n times the speed of propagation of the wave divided by 2 in this case. And so you have n times 2 times L divided by 2 times L. And that's So the first harmonic, the fundamental, is when n is equal to 1. The second harmonic is n equal to 2, and so on. So all string instruments that you hear actually you generate the right frequency, the right tone, by creating the first, usually the fundamental frequency. So you adjust the length of the string that is going to oscillate according to what frequency you want to hear. But usually, in addition to the first harmonic, you have other frequencies that are going to be present if you create an oscillation, just spontaneous oscillation. But the other harmonics are going to be with much lower intensity sound. And what is much lower intensity depends upon the shape of the entire musical instrument. Now, different musical instruments have different shapes, and therefore, those second and third harmonic frequencies are going to be represented with different volume. And as a result, this is why a violin sounds different from a guitar, or a violin sounds different from a cello, just because the higher harmonics are going to be represented with different value. Again, the highest volume is going to be in the fundamental, in the first harmonic always. Yes.
In violin, also there's a thing called harmonic notes where if you don't push down all the way, you push very lightly, you get a different, really high pitched kind of note. Is that related to this, or is it just called?
So I have to see how it works, because I really don't play violin. But if you have a string with one end that is fixed and the other end may not be completely fixed, in that case, the pattern of standing waves is going to be different, not what is given here. And we're going to talk actually with standing waves with open end tubes or so. Now, knowing all of this, we can solve some problems from the homework assignment, but we have only 2 minutes left. So let's start talking about standing wave patterns in a tube. So if you can create a sound, let me see, probably the way to, well, you hear some sound, and this sound is again is a standing wave produced by sound waves that propagate in this direction and in this direction, in two opposite directions in the tube. Now, if you have pipes with two open ends, you can represent the sound wave that is a standing wave in a pipe with two open ends with the following diagram. Here is the pipe, and if the two ends are open, the sound wave is going to have antinodes at the open end, and the other end is also open, so it has to have antinodes at the two open ends. This means that you're going to have highest amplitude of oscillations, highest amplitude of pressure variation at the two open ends, and therefore you're going to have no variation of the pressure exactly in the middle. So this is the first harmonic, lambda 1, and you can see that it is again 2 times the length of the pipe L. Notice that unlike the string with 2 fixed ends, where notes appear at the 2 fixed ends, here the notes are at the 2 open sides of the pipe. In a similar manner, a second harmonic is going to be formed, again following the rule that the second harmonic must have antinodes at the 2 ends. So the second harmonic is going to, so look at the diagram that is on the left. Well, so this is in terms of displacement and pressure, that's not good. But this is the pattern, let's say, of the standing wave, either looking at well, we don't do displacement in this class. This slide is from different textbooks, so it is not probably appropriate for us. Actually, the next one actually is probably exactly what we want, right? Here is the next one. So this here you clearly see the shape of the first harmonic. You have antinodes at the end and node at the middle. In a similar manner, the second harmonic is going to be half a wavelength longer. So the second harmonic is going to have wavelength exactly equal to the length of the pipe, and so on. At the end, the wavelength of the nth harmonic is going to be given exactly with the same formula as the string with 2 fixed ends, and rewriting that formula in terms of frequency is going to give you exactly the same frequency. The things are going to change completely when you work with a pipe that has 1 open and 1 closed end. And we're going to talk about that case on Friday. See you on Friday. Any questions, any remarks? In that case, we're going to finish the chapter on Friday. Thank you. Welcome. You too. Yeah, just give me a second.